Dust the math club, I will dust the math club. Dust the math club till the dust is gone.
Hey there, Dusty. Glad to see you're finally doing some chores around here. What's got you in such a good mood?
Oh, hey, Pete. I'm excited because I know that today we're going to talk about Fermat's last theorem, one of the great unsolved questions of the past few hundred years, and how it was finally proven during our lifetimes.
Awesome. I'm really looking forward to it too. It's pretty much the greatest story of all time.
It's that good, right?
Are you kidding? Fencing, fighting, torture, revenge, giants, monsters, chases, escapes, true love, miracles.
Really?
Oh, dude, that's the plot of The Princess Bride.
Oh,
But don't fret, little doodle. Even though this story doesn't have giants and monsters, it does have a lot of exciting twists and turns and plenty of fascinating math.
okay. So how does it start?
Well, before we dive into the story, allow me, if you will, to set the mood.
Okay.
Alexa, initiate Fermat protocol.
Fermat protocol initiated.
Alexa, what's going on?
System logs show the Fermat protocol was 100% successful. You have arrived at the precise temporal coordinates that you requested, Pete.
Arrived? Where?
Toulouse, France, in the year 1637.
What?
Oh boy.
Oh boy. No, you do not get to oh boy your way out of this. What is going on?
Yeah, I think something might have gone wrong.
Might have gone wrong?
Well, I was trying to use Alexa to create some nice, mood-setting ambiance for the episode. You know, background noise and sound effects and stuff. So I asked for France in 1637. But I forgot that after she got that upgrade last year, she can literally send us to France in 1637.
Wait, so we're actually at the time that Fermat wrote his last theorem?
Well, actually, Noah, spoiler alert. This wasn't even his last theorem.
Hold on to that nugget, Alexa. We'll get to that part of the story when we get to it.
When we get to it, when is that, do you think? In like 5 minutes, real time? He's probably writing the darn thing down as we speak. And even more importantly, how are we going to get home anyway?
Settle down, dude. It's okay. Alexa can get us back home anytime we want. In the meantime, I was just going for some great background noise. But this is so much better. We could actually record the episode on location.
I guess.
Look around. Here we are in the 1630s. Fermat is here somewhere. Alexa, where is Fermat right now?
Pierre de Fermat is currently 1.77 miles from your location.
Fermat is a mere 1.77 miles from here. He's probably scribbling in the margins of Arithmetica as we speak.
Okay.
And just think of all the great things we can do in 1630s France.
Yeah? Like what?
Like, Alexa, what are some things we could do in 1630s France?
Oh, there are so many good choices. You could meet some of the philosophers, scientists, and mathematicians who were laying the groundwork for modern thought, like René Descartes. You could take in a musical performance featuring compositions of the early Baroque period. Or, if you're feeling morbid, you could even attend a public execution. According to my records, at 2:30 this afternoon, heads are gonna roll.
Alexa, we are not going to a guillotine show. But some of those other options do sound pretty cool.
Suit yourself.
Or we could go and see what we're going to talk about in this episode and check in on Fermat as he's writing his last theorem.
Again, Noah, this is not really his...
We'll get there, Alexa. Tell you what, Noah, it's a beautiful French day, and we've got a 1.77 mile walk ahead of us. Why don't we make our way to Fermat's place and see if we can get a peek at his work? I'll tell you all about it on the way.
Oh, hey, do you think we should bring him something? Like maybe a baguette?
Ooh, and some brie.
So, Pete, before we get too much into the story, let me ask you first, what does Fermat's last theorem actually say? Like, what is it?
Good question. Fermat's last theorem is a certain claim made by French mathematician Pierre de Fermat back in 1637, and it remained unproven for more than 350 years. It starts out with an equation, x to the n plus y to the n equals z to the n, where n is a whole number exponent, which is greater than or equal to 3. So for example, x cubed plus y cubed equals z cubed. That would be the smallest case, n equals 3. And so Fermat's last theorem states that these equations for every exponent greater than or equal to 3 have no non-trivial integer solutions.
Well, I want to ask you in a sec about those non-trivial solutions, but first, this sounds an awful lot like the Pythagorean theorem. I mean, I know that in the Pythagorean theorem, x squared plus y squared equals z squared, the exponent is 2. And you said that here, the exponent has to be 3 or greater. So obviously, the Pythagorean theorem is sort of a special case that isn't included here, but it does seem like there's some similarity.
Yeah, for sure. And my guess is that Fermat was very well aware of the fact that this statement is generalizing the Pythagorean theorem by simply altering the exponents. But there's a radical difference.
I see what you did there, Mr. Radical.
Yeah, and in the case of the Pythagorean theorem, we know there are infinitely many solutions. In other words, numbers a, b, and c such that a squared plus b squared equals c squared. 3, 4, 5, for example, is one very well-known solution.
Right. I remember talking about all of these Pythagorean triples in one of our very first episodes called Triple Play.
Yeah, and 5, 12, 13 is another, 8, 15, 17 is yet another, and there are, in fact, infinitely many solutions to that equation, provided the exponent is equal to 2.
Right. But what we're saying is that what Fermat was concerning himself with was this general structure of the equation where the exponent is 3 or more.
Exactly. And so you might say, well, Pete, I can think of a solution when n is equal to 3. I'll set x equal to 1, I'll set y equal to 0, and I'll set z equal to 1. And sure enough, 1 cubed plus 0 cubed is equal to 1 cubed.
So it sounds like there are solutions that work, but you can't really make a triangle with a side of 0.
Yeah, and although we're not really making triangles anymore in the case of Fermat's last theorem, you highlighted exactly what's at the heart of this expression, non-trivial solutions. We can always set one of the variables equal to 0 and find lots of ways to make the other numbers work. We're interested only in cases where none of the numbers is 0. So 1, 0, 1 is ruled out. That would be called a trivial solution.
Believe me, nothing is trivial.
I see. And Fermat's last theorem stated that there were no non-trivial solutions for any exponent 3 or greater.
That's right. Whether the exponent is 3 or 73 or 73 million, Fermat is saying there aren't any solutions. You can look for as long as you want, but you're not going to find any.
And just to make sure that we're all clear and everybody's following along, what we mean is that if you take an exponent like 73, there are no solutions means there are no 3 numbers where the first number to the 73rd power plus this second number to the 73rd power equals some third number to the 73rd power. That's what we're saying?
That's right. And specifically, we mean there are no integer solutions.
What does that mean?
Well, there are plenty of solutions if we allow some of the variables to be irrational. For example, suppose I set x and y both equal to 1. Then since 1 cubed plus 1 cubed is 2, I can choose z to be the cube root of 2. Then I get this solution. 1 cubed plus 1 cubed equals the cube root of 2 cubed. But Fermat wasn't interested in irrational numbers. Each of the values had to be an integer.
All right, so he wrote this down in 1637, but it sounds like this kind of problem had been around for quite a while. Like way back in ancient Greece, they were already finding these Pythagorean triples. So how far back do we have to go to really get to the beginning of this story?
Well, in some ways, we should go back to the time of Pythagoras, which is roughly thought to be 570 BCE up through 495 BCE. So we are some 2,500 years ago, and Pythagoras, along with many other Greek mathematicians, was studying geometry and numbers and the connections between them. And this is the origin of the famous Pythagorean theorem, which says if you have a right triangle and you square the lengths of the legs and add them together, you'll get the length of the hypotenuse squared. This is often abbreviated by simply saying a squared plus b squared equals c squared. Well, a few hundred years later in the Elements, Euclid gave a complete proof of the fact that there are infinitely many right triangles, all three of whose sides are actually whole numbers. These are the so-called Pythagorean triangles. So we've known for more than 2,000 years that the equation a squared plus b squared equals c squared has lots of non-trivial integer solutions.
Okay, so it sounds like Pythagoras did some work a couple hundred years later, but still in ancient times, Euclid was doing some work. There's over 1,000 years between the time of Euclid and the time of Fermat. What's going on in the interim?
Yeah, Fermat was born in 1601 in France and lived until 1665. So we're well over 1,000 years later. And somewhere in the middle, there's a connection. And that connection is a Greek mathematician named Diophantus, lived in Alexandria, Egypt, sometime between the years 200 and 285. And it is thought that roughly around 250, he wrote a book called Arithmetica.
Okay, wait a minute. Diophantus wrote the book Arithmetica? Because a few minutes ago in our sketch, I remember you made a comment about Fermat scribbling in the margins of Arithmetica.
Yes, and that is the connection. So Diophantus wrote this book in Greek in 250. And over the course of the next 1,400 years, roughly, that book is preserved. Some parts are missing and lost to history, but a big chunk of it is preserved. And in 1621, a French mathematician named Claude Bachet makes a Latin translation of Arithmetica and publishes it in printed form. And Fermat acquired a copy of that book. And that is the Arithmetica that he scribbled his notes in.
Okay, well, that's interesting. It makes me wonder, why would Fermat want to have a 1,400-year-old mathematics book?
Well, let's put ourselves into the mindset of what somebody like Fermat was experiencing. So it's France in the 1600s. We are smack in the middle of the scientific revolution. That was kicked off with the work of Copernicus in the 1540s, right? Calculus has not yet been invented. In fact, Newton won't be born yet for quite some time. He was born in 1643. So Fermat is coming of age. He studies to be a lawyer, but he's very interested in mathematics. Math and science are in the air, at least in intellectual circles. Fermat did have some connections to the French intellectuals living in Paris, and he has acquired a copy of Arithmetica. He probably was very well aware of other ancient Greek mathematical texts as well, like, for example, Euclid's Elements. So it wouldn't have been uncommon for somebody like Fermat, who came from a wealthy family, who had access to education, and who had a love of mathematics, to be thinking about things like this.
Okay, so is it relevant to ask what was the focus of this book by Diophantus?
Oh, yeah. And well, Arithmetica is an early treatise in algebra. It contains a large number of problems which essentially state various forms of algebraic equations. And then the solutions of those equations are found and methods are presented for, in general, solving these kinds of equations. Here's an example from the book. Find two integers whose sum is 100, given that one of the integers is 40 more than the other. So very standard kind of algebra problem.
Spoiler alert, 30 and 70. Nailed it.
You really did. That's something special. So this book is full of problems like that. And Fermat would have been aware of this. And those kinds of problems and the equations that they generate have become so central in the field of abstract algebra that they have earned a name of their own.
By what name are you known?
There are some who call me Tim.
They are called Diophantine equations. And in general, problems of this sort are called Diophantine problems. they're super relevant even today in the year 2025.
Okay, and this question that became the focus of Fermat's last theorem, the question of are there any non-trivial solutions to x to the n plus y to the n equals z to the n if n is a whole number that's 3 or greater? Is that one of these Diophantine problems that Diophantus put into Arithmetica? Is this where Fermat kind of started wrestling with it?
Actually, no. So it is a Diophantine problem, but it is not one that Diophantus himself put into Arithmetica. As far as I know, it is sort of Fermat's problem. Now, it's natural enough that other people at the time might have wondered about it, but Fermat not only wondered about it, he actually wrote down in the margin of his copy, his personal copy of Arithmetica, that there is no such solution to this equation for any exponent greater than or equal to 3. And I have a truly marvelous proof of this fact, but it's just too big to fit in the margin, so I'm not going to write it here. How is that for a teaser?
Okay, but that kind of leaves me confused because you told me that Fermat's last theorem was finally solved within our lifetime. I think you said it was back in the 90s sometime. So if Fermat had a proof of it 350 years ago, why do we say that?
Good question. And there's a lot to unpack here.
So we unpacked our adjectives.
So let me start by saying, yes, Fermat's last theorem has been proven, and it was proven in 1994 by Andrew Wiles. So many hundreds of years later, past Fermat, right? Set that aside, and we'll get to that later. But in 1637, when Fermat wrote this down in Arithmetica, as far as we know, nobody saw it. Nobody saw that comment for almost 30 years after Fermat had died, when his son set about the project of publishing a new version of Arithmetica that included all of his father's notes. That's when this problem statement was first sort of surfaced to the world at large. And in fact, it is thought that Fermat did not have a proof of this statement, except in the case when the exponent was equal to 4.
Meaning that he had proven there were no non-trivial solutions when the exponent is 4, but we don't think he had proven it for all the other bigger exponents?
That's right. And now it's a bit speculative. Maybe Fermat did have a proof, but the techniques that Andrew Wiles used in his proof would simply not have been available to Fermat. And no mathematician since 1637 has been able to imagine a proof that Fermat could have had in hand. It just seems exceedingly unlikely.
So I'm going to ask you to speculate here because we obviously don't know the answer to this question, but do you think Fermat was just boasting about something he didn't really have, or do you think he thought he had it and he was mistaken?
I think it's possibly a little bit of both, but I think it might more be the latter because, first of all, Fermat was an exceptional mathematician. He was an amateur mathematician. His employment was as a lawyer and a government official. But when it comes to his mathematics, he was absolutely first rank. He was in communication with the great minds of the day, including people like Mersenne, Descartes, Carcaville, Pascal, any number of mathematicians who were around at the time. So he was doing very good work, and he was right about a lot of things. And he had developed a technique called the method of infinite descent that he used to prove the theorem when n is equal to 4. So my guess is that Fermat thought that his technique of descent would be able to handle all of the exponents. But later, he wrote a letter, and he seemed to suggest in the letter that he didn't quite have a descent proof for n equals 3. He said, hey, I think descent works here, but there are some details that need to be checked. So my guess is that Fermat thought that maybe his technique would work, but he hadn't confirmed it.
All right, so what is this method of descent, and how did he use it to prove that there were no non-trivial answers when n equals 4?
Yeah, so the method of descent is simply a proof technique that Fermat developed to help show that certain equations do not have solutions. And so the way it worked for him in the case of n equals 4 is he said, suppose I have a solution to that equation. Then by applying his process of descent, he was able to arrive at a contradiction, which implied that his original assumption that there was a first solution to begin with could not possibly be true. Yeah.
So just like we talked about in our proof of concept episode, this is a proof by contradiction.
Yeah, and at its core is another theorem that he proved, which is related to the Pythagorean theorem. And this is one that he actually did leave a proof for in his notes.
And when you say in his notes, you mean in the margins of his copy of Arithmetica?
Yeah, in that copy of Arithmetica that later got passed on to everybody else through the edition that his son published.
Okay, and what's this other proof that he did write down, and how is it related to our story here?
Yeah, it's actually really interesting. So this result is very Pythagorean in nature, and it starts off with a right triangle, all of whose sides are whole number lengths. So in other words, a so-called Pythagorean triangle. And his result is that no such triangle can have as its area a perfect square.
So, like, for example, there doesn't exist a Pythagorean right triangle where the area is 64 square inches.
Yeah. And so if we look at some examples of Pythagorean triples, because remember, those are the trios of numbers that describe Pythagorean triangles, right? So let's look at the most familiar example, 3, 4, 5. So the area of that triangle is 1/2 3 times 4. So 3 times 4 is 12. That triangle has an area equal to 6. Definitely not a perfect square.
And what Fermat did here is went on to prove that no matter which Pythagorean triple you use to make a right triangle, you'll never get an area that is a perfect square.
Exactly. And that connects via some algebra. It connects to his observation about the last theorem with n set equal to 4.
The name of the game is Connect 4.
So by connecting those two and using a descent argument, he essentially proved that there are no non-trivial solutions when n equals 4.
You just mentioned Fermat's last theorem again, and it reminded me that even though we teased in our sketch over and over and over that it was not actually his last theorem, you haven't actually told us yet why it's called that.
Yeah, and that's an interesting story in its own right, but we're going to need to introduce a new character to the stage, if you will, and that person is Leonhard Euler, the phenomenal Swiss mathematician who was born in 1707 and lived until 1783.
Well, yeah, I remember talking about Euler with you a few times in the past on various episodes.
Yeah, now, unlike Fermat, Euler was a kind of publishing machine. So during the course of his professional lifetime, he published a total of, get ready for it, 866 scholarly articles devoted to mathematics and science.
Compared to Fermat, who didn't publish any articles because he was a lawyer and not a mathematician.
Well, we've got two kinds of historical publications from Fermat. Those are either letters, private letters that he wrote to other intellectuals and other mathematicians. Again, those were not intended for scholarly publication. And on the other hand, the notes that he wrote in his copy of Arithmetica, which was only published after his death by his son. So he was definitely not thinking about publishing his work. In fact, he deliberately withheld publication because he challenged other mathematicians by saying, hey, I know something. Did you know that a Pythagorean triangle can't have a perfect square area? And then he would just leave it at that. Like, hey, could you show this?
Here's what I'm wondering now. Euler wasn't even born until 40 some odd years after Fermat died. What's his intersection with the story that we're telling?
So Euler actually was a professional mathematician. That was his life pursuit. And he had formed a relationship with a Prussian mathematician named Christian Goldbach. Goldbach was kind of his mentor and friend. And in 1729, so at this point, Euler was a young man, 22 years old, Goldbach writes in a letter. And in that letter, he says, hey, there are these interesting numbers that Pierre de Fermat defined, and Fermat made a claim about them, and nobody knows how to prove it. And I think you might be interested.
And was Goldbach's suspicion correct? Was Euler interested in trying to tackle some of this?
Oh, yeah. This is actually how his lifelong obsession with number theory began. So Fermat was looking at a certain sequence of numbers, which have now come to be known as Fermat numbers. But these are positive integers that are one more than a certain power of 2. Specifically, you raise 2 to the power 2 to the n, and then add 1 to the result. Fermat's claim was that every number of this form is prime.
Okay, wait a minute. 2 raised to the power of 2 to the n, then plus 1. Maybe it would be a good idea to do some examples to be clear about what these Fermat numbers are.
Yeah, sure. So let's keep it simple and start with n equals 1. What's 2 to the n in this case?
Well, that would just be 2 to the first power, which is 2.
Yep. And so now you want to take 2 and raise it to that power that you just calculated. So what's that?
Well, that's just 2 squared, which is 4.
Right. And finally, we add 1 to that to get the Fermat number.
So if we add 1, we get 5. Is 5 the first Fermat number?
Yeah, it is. And this lines up with Fermat's claim since 5 is prime. Now, what do you think we'd get if we try n equals 2?
All right, give me a second. So 2 to the second power is 4. And if we raise 2 to that power, that's 2 to the fourth, which is 16. And 16 plus 1 gives us 17. So that must be the second Fermat number.
And 17 is very famously known for being prime. So that's an example where Fermat's claim about the primality of these numbers is actually confirmed. For n equals 2, this number is prime.
Okay, so the example we just did that led to 17 led to a prime number. And Fermat's statement was that every time you follow this equation, whatever n is, you're going to get a prime number. So if I'm following this, then the next exponent would be 8, right?
Yep.
All right, so 2 to the 8th is 256 plus 1 gets us to 257, which also seems like a prime number. Is it?
It is a prime number. And Fermat went one step further and computed the fourth number of this sort, which is 2 to the 16th plus 1. I looked this up before we hopped on the call, and that is 65,537, also prime. And so Fermat said, look, these are all prime. And he left it at that.
Was Fermat saying that he had a theory that they were all prime, or did he state it as if he had proven it?
Well, what was typical of Fermat was to state it as though it was known to him. It was possibly even one of these things that he would brag about. He'd shoot off a note to Descartes like, hey, Descartes, I know this thing. These are all prime. Can you prove it? That's kind of what I suspect was the case.
And I suspect that the reason we're talking about Euler now is because he came onto the scene and either confirmed or disproved what Fermat had said there.
You're exactly right. Now, in 1729, he gets this letter from Goldbach. And at first, Euler's got nothing. He's not able to really get a toehold on it. And then in 1732, he lets Goldbach know Fermat was wrong. I have a proof. I have demonstrated that the next number in this sequence, 2 to the 32nd power plus 1, which is more than 4 billion, by the way, is actually composite. It's divisible by 641.
I just want to take a moment just to acknowledge how amazing it is that he was able to figure that out in the time where he lived. I'm thinking back to our episode, Finding Primo, where we talked about how current day mathematicians search for these really large primes and the kinds of computer algorithms they have to use in order to check if they're divisible by anything. And the fact that Euler was able to say, no, this gigantic number is divisible by 641 back in the 1700s, it's just impressive, don't you think, Pete?
Oh, it's totally impressive. And we actually know that he did not prove this by simply checking. Well, let's try 131. Is that going to divide it? He didn't do something like that. Instead, he invented a framework for understanding divisibility, and then he applied his results and then said, lo and behold, this number must be divisible by 641. In fact, he had proven that this Fermat number must be divisible by some other number of the form 64n plus 1. And he simply marched up, well, what if n is 1? What if n is 2? And he got up to n is 10, 641. Boom, found a divisor.
So back for a minute to Goldbach, the person who wrote that letter to Euler, initiating his lifelong interest in Fermat numbers. Is this the same Goldbach we talked about a few episodes back, who the Goldbach conjecture is named after?
It's one and the same. And just to give a little reminder of that, Goldbach's conjecture, which is still to this day unproven, states that every positive even number can be written as the sum of two primes. So 4 is 2 plus 2, 6 is 3 plus 3, 8 is 5 plus 3, and so forth. This is the same Goldbach that made that conjecture that still has no proof to it.
Didn't Euler feel like tackling that one? I mean, what's going on with this slouch?
Oh, I'm sure that Euler spent some time thinking about Goldbach's conjecture because Euler made a number of really important observations about perfect numbers, and perfect numbers are intimately tied into the Goldbach conjecture.
Okay, then circling back to Euler at this point, after he disproved Fermat's conjecture, I'm guessing that the reason he's getting brought up in this story is because he then went on to take a look at some of Fermat's other conjectures and theorems.
He did. And, as we had said, Fermat was not in the habit of leaving behind proofs of any of his claims. Euler, on the other hand, was very interested in proofs and writing them down and circulating them. And so he sort of set himself the task of working through this material. Now, of course, Euler's got many irons in the fire. He's not just looking at Fermat's work. He's doing many, many things. But among that body of work are these tasks of proving or disproving Fermat's claims. And Euler was able to essentially prove or disprove all of them, with one very notable exception.
Well, based on the fact that you already told us that Andrew Wiles was the one who proved Fermat's last theorem in the 90s, I think we know where that exception lies.
Yeah. And in fact, that exception is what gives Fermat's last theorem its name. Euler did give a proof when n is equal to 3. So using a method similar to Fermat's method of descent, Euler did prove that x cubed plus y cubed equals z cubed has no non-trivial solutions. So he did advance the state of the art on this conjecture, but that's all he was able to do. And because all of the other results that Fermat had postulated or conjectured, at least the important ones, Euler was able to resolve, except for this one. It was the last thing that still stood from Fermat's body of work. And that's why it's called Fermat's last theorem.
Oh, now I get it. I'm really starting to think that the way to prove Fermat's last theorem isn't to prove that there are no non-trivial solutions for each value of n one at a time. You're telling me how Fermat himself proved it was true for 4, Euler later proved it was true for 3, but good Lord, are we going to have to prove this thing by going, how about 5? How about 6? How about 7?
Yeah.
I mean, there are infinitely many numbers up there. Even if you prove it for 100 of them, you've barely made a dent.
That's an excellent observation. And it sounds daunting, right? If we have to prove these results one exponent at a time, we're never going to get to the end of the line because there's always going to be more to do. What we need is a new idea, an approach for eliminating multiple exponents all at once. So let's summarize the state of things at this point. It's the mid to late 1700s. Fermat has written this conjecture in the margins of his copy of Arithmetica, and his son publishes those notes in 1670, a few years after Fermat's death. That information makes it into the minds of Christian Goldbach and Leonhard Euler, who then start the work of advancing the theory. And a lot of progress is made. However, no general framework for cracking Fermat's code, if you will, is present at this time. In 1783, Euler dies. And with that event, his juggernaut of mathematical work comes to a halt. However, at this very moment in Paris, there's a 7-year-old girl named Sophie Germain who will grow up to play a crucial role in the next part of the story. She'll go on to study mathematics and will take the first steps toward a general approach for dispensing with many exponents simultaneously. And it's exciting, and it really marks the beginning of the modern era.
Oh man, this story just keeps getting more and more interesting. Go on.
Well, there's a lot more to say, and there are a lot more people to bring onto the stage, but I think we've said enough for now. How about this? What if we pause here and save the rest of the story for the next episode?
Oh, all right. You got it. I am really looking forward to part 2. And Math Club, I hope you are also on the edge of your seats excited and looking forward to part 2 of this conversation. We will be back with that in just a few weeks.
I'm looking forward to it, Noah. All right, Math Club, we will see you for part 2 of this most astonishing journey.